All right, recording is rolling. So it is Wednesday, January 25th. So we're going to do ray diagrams for refraction day and also look at telescopes, how telescopes work. So recap from the last few days. There's no few days back, we were looking at reflection. We did some ray diagrams for reflection, so like where would the image be? And compare that to like a cosmetic mirror, or you're trying to explain this, for example. Those are both concave mirrors. Then we flipped over yesterday and we're looking at refraction. We were looking at Snell's law. We were looking at, okay, here you go. Here's refraction and Snell's law. Okay. And today we're going to do the ray diagrams for those and a few other things too. And then in the class, I've got some illusions for you guys. I'm not going to be here tomorrow. You guys are going to have a substitute. So there's like a professional development activity thing going on. So probably a lot of your teachers are going to be out tomorrow. So I'll have a set for you guys then. Okay. Oh, and guess what I found? And this is like on my demo shelf, but okay. So I've got some polarizing filters. So these will polarize light in one direction. In fact, you guys might have some sunglasses possibly that are also polarized. Did I play the Paul Hewitt video for you guys on polarization? Do that? No. Oh, okay. Yeah. So some classes I had a few spare minutes. Okay, but this will polarize light in one direction. This is also evidence that light is specifically transverse waves, because transverse waves can be polarized. Versus you can't use this with longitudinal. Okay, you guys see this right here. So like if this is polarized vertical and this is polarized horizontal. These guys see how kind of the light gets through. But if I switch it to vertical and vertical, okay, well, the light gets through, right? So if you have some sunglasses that are polarized, and it's kind of hard to see here. I don't know if this. Oh, actually, you can kind of see that. Okay. It's like you can see through there, but not that way. Okay. You put these in front of a computer screen or another set of polarized glasses. You can do the same thing. Right? It's just easier to see with these filters like that. Okay. Hey, which way do you think sunglasses are polarized? Would it make more sense to have these polarized basically horizontally or basically vertically? Remember, whichever way it's polarized, it lets light through that way. So imagine you're driving on the road. Maybe you're driving west into the sunset. The sun's kind of in your eyes. You got a bunch of horizontal light coming. You got the horizon horizontal. You got the sun like and you block out all this excess light. Do you want a horizontal polarization to let all that excess horizontal light through, or do you want a vertical polarization? What makes more sense? Yeah, vertical, right? You guys are saying vertical, right? Okay, so that's probably what you want. Okay. Or how about this? Can you guys imagine? What if you had one lens that was like polarized horizontal, and the other lens that was actually wait, which way would this be? Now I gotta check. Gotta see it in real life here. Okay, so that blocks it. So this must be horizontal this way, and then this one must be vertical. Or I think, wait, is that right? Hold on. No, sorry, it's blocked that way. That means this one would be horizontal now. Right, and this one's vertical. Okay, there we go. Okay, you guys can see the difference there. Okay. So why would you want one horizontal and one vertical? Like what would that be useful for? Say I had each of these like left eye, right eye. Why would you want a different image to go to your left eye versus your right eye? That would be really useful if you were watching a 3D movie. You guys think 3D movie? Right. Okay. Now, actually, it's a little more complicated than that. There's some kind of like spiral polarity, but that's the basic principle, right? Is that you want different polarization. So 3D glasses work, right? Different information into each eye. If you go back close to 100 years ago, they used to have like red and blue. That throws the color off too, but has something to do with like getting a different image into each eye. Okay. So let's do ray diagrams for lenses, refraction. So this is a continuation from refraction and Snell's law from yesterday. Now we're going to do like a lens application of this. You guys got a paper on your desk? You guys got paper? And so on this paper, write your name. Okay. I'll have you guys turn this in by the end of class today. Okay. So your name is on your paper? You guys got a name? You guys going to get points for this? And then title this ray diagrams refracting lenses. Actually, that's what we'll do on the front, and then the back of this page will look at how telescopes work. That's what we're going to do. Okay. So we can fit 3 of these diagrams on page, just like the ray diagrams you already turned in for reflection. Okay. So the ray diagrams we did in the past few days are all working with like reflective surfaces like mirrors. That's not what we're about to do right here. We're about to look at lenses, like refracting lenses. And there's 2 ways that we can have lenses refract. Kind of analogous to the mirrors. Like the mirrors could be convex or concave, right? But the lenses are going to be either converging or diverging. Let me pull up Paul Hewitt's book and show you guys the Paul Hewitt drawing of this. Okay. So, oh look, eyeglasses. I bet if you're wearing eyeglasses or contact lenses, that what we're about to do is really applicable to that. Okay. So here's a converging lens. See how it has like this type shape, converging lens. Okay. So if you have a bunch of parallel light rays, see how they all converge to a focal point. Versus a diverging lens. See how a diverging lens is shaped like this? Okay, where it's like thick on the outside and thin on the inside. So if you have a bunch of parallel rays, they'll all diverge. That's a diverging lens. Okay. Right. So what's the connection to eyeglasses? Well, you might be nearsighted or farsighted if you're wearing glasses, right? Those are 2 opposite possibilities. Okay? So if your eye is shaped a little bit different, right? So if you are farsighted, let's start with that one. Your eyeballs squeeze a little bit too short, so the light is not converging exactly where it should. So you want to wear a corrective lens for that. What you want to do is have a converging lens, and you can tell because it's really thick in the middle and it's thinner closer to the rims. Zoom in on that so you can see that a little bit better. Okay. Versus if you're nearsighted, well, your eyeball's a little bit too long. The light converges a little bit before it hits your retina. So how do you correct that? Well, you would correct that with a diverging lens. Right. See, it's really thick near the rims and it's thin kind of near the middle. All right. So there you go. There's eyeglasses for that map. Okay. All right. So let's do. Okay. So everybody did this so far. You guys got a name on your paper. You got it titled "Ray Diagrams for Refracting Lenses." You have 3 horizontal lines going across the paper. Okay. Because we're going to do 3 individual scenarios. Okay. These first 2 are going to be converging lenses. So converging lens, converging lens. Okay. This third one will do a diverging lens. Okay. Go ahead and draw those. Okay. So converging lens could look this about. Okay. Do the same thing here. Do a little bit different setup here. Okay. And then your diverging lens will look more like that. All right, that's pretty good. 2 converging and a diverging is what we're doing. Okay. And here's the center point for each one of these. And the center point is going to play a role in how the ray diagrams work out. Okay, so have that center point. Okay. Oh, also you need a focal length for each one of these, like a focal distance. If you guys remember with mirrors, like the more tightly curved the mirror, the closer the focal point was to it, and the closer it was to a plane, the focal point got like infinitely far away. Okay, so just some context there. Okay. This first one, let's see. So I want to do this. Oh, let's just do one at a time here. Okay. This first one, maybe I'll put the focal point. Right. Say about 7 or 8 centimeters out. I think that should work. About 7 or 8 centimeters. Right there. Okay. Oh, and notice I do like 2 focal points. You guys see that? Okay. Focal point. Because I mean, this is like a lens. It's transparent. It's symmetrical. So I mean, if there's a focal point on one side, it's going to be on the other side too, right? Okay. Now that was not true necessarily for mirrored surfaces because there's only one side of a mirror that really counts, right? But a converging lens, like a lens, go through both sides. Okay. Right. And what I'm going to do for this first one is put an object inside that focal distance. And to help you out a little bit, let's make this guy, don't make him super tall, make him, if anything, kind of err on the short side. So drew an object right here. There's an object. He's inside the focal length, inside the focal length. Okay. And since this is a lens, let's have this. I'm going to draw an eyeball over here. So like there's an eye over here, like an observer. Okay, looking at the situation. Okay. What do you see? This guy right here. What does this guy see? This eyeball guy, this observer. See, looking through this lens at this object inside the focal length. Is that? Now we're going to follow a series of rules for refracting lenses for this ray diagram, which is a little bit different than the rules for mirrors. And we're going to find out where is the image. But before we do the ray diagram, let's actually do the science and figure out straight up what the answer is going to be. Let's do the empirical bit first, the science bit. Because look what I have here. This right here. This is a converging lens, just like I drew. My drawing's a little bit exaggerated, but you guys get the idea. Hey, what's this device called? Is that called a magnifying glass? Ooh, it should magnify, right? You guys see how the image is like getting blowed up bigger? Right? Or see if you're at home. Let me see do this at home for you guys. If you're watching this on video, spin my hand a little bit. All right. And so this is for the video camera at home. Okay, you guys see it getting magnified, and then for you guys in class, there it is. You see it getting magnified. Okay. So the ray diagrams, if they really describe something about the world, they should be describing magnifying glass. Okay. Let's see if that is true. Where's I'm going to switch over to pink ink. You don't have to switch color if you don't want, but you can do the pink ink for the rays. All right, so everybody get this so far? So let's have one ray going parallel to the ground, skirting across his head. Zip. I mean, we did that yesterday too, right, for the mirrors, but now something a little bit different today. Well, when this ray of light hits this surface, going from the air into the glass, isn't it going to refract a little bit? I think it's going to refract this way a little bit. And then when it exits the glass and goes back into the air, it's going to refract a little bit more. So now this is a converging lens. You see I'm rotating the ruler this way. How much should I rotate it? Oh, well, that's what the focal point is for. So we're going to merge this here. Can you guys line this up with the focal point? Zip, and that ray light would go there. So if you shine in a laser this way, shine a light this way, it should bend it down this way. Okay. And then this eyeball here, looking at this ray, says, okay, hey, this ray light looks like it came from, I'm going to add this a little bit, from back here. That's where it looks like it came from. Right? Wouldn't that be true? Okay. So that's what this observer thinks. Oh, it looks like it came from like back here. Let me show you guys that too with this converging lens and this laser. Okay. So say like it shined down a laser dot. Okay, so you guys see where the laser dot is, right? Okay. But if I put the converging lens between the two, then shouldn't it bend it like like this way, like bend it like down? Right? I think it should if I shine it like right here, right? Okay, now this is kind of tricky just because you guys are like stuck in this certain place, but let's see if I can get this at least to work on camera. But so put the yeah, I see that happening. I see that working. Okay. If you guys can see here, I'll put some dots on the paper. So I'm aiming it like bam right there. That's where I'm aiming it. Okay, and then when I put the lens here, it jumps. It jumps. It jumps to like right there. That's where like it jumps to. Yeah, exactly like that ray diagram shows. Okay. Okay. So now we need another ray of light to figure out where the image is going to be. Let's go from the top of his head. Okay, now this rule is unique to the lenses that we're doing. So this is a new rule. You guys haven't seen this yet. We're going to go from the top of his head through the center of the lens. And that one, it might refract a little bit there and a little bit there, but it's basically negligible. So we're going to simplify and just say it's a straight line. It's basically a straight line. Straight line. Okay, from the top of his head through the center of that lens. Okay, see that? Connect those 2 points and extrapolate out. Right? Look at that. So is that parallel to the ground that refracts through this focal point, and then you extrapolate backwards with this dashed line. Okay. And then we made a second ray, and it's just one straight line from the top of his head through the center of the lens. Do you guys see where those rays intersect right there? See where they intersect? That right there is the image. Put his feet on the floor, just like we've been doing all along, like yesterday. Image right there. Hey, that is a magnifying glass, isn't it? Because this observer views an object that's blown up really big. That's a magnifying glass. I'm going to label that. I'll call that a magnifying glass, magnifying glass. Everybody got that? All right, now the second one, what I want to do is maybe use the same lens, but I'm going to take the object and move them outside the focal point. And I'll make one other alteration to help us with that, which is I'm going to move the focal point in, say like proportionally, he'll be like further out. Okay. So I'm going to move the focal point in. See how I'm do this here. Okay. Let's say I'll go about let's say 4 centimeters out. So I'll go 4 centimeters out there, 4 centimeters out here. I think it's gonna work. Okay. Focal point, focal point. Okay. And I'm gonna put this object, let's say at least twice as far out. So at least 8 centimeters out. So I'll put it like out here. So here's the object. Right. So the main difference between what we just did and what we're about to do is the first one, the object is inside the focal distance, and that magnified it, so that worked as a magnifying glass. Okay. In the second one, I'm just going to move the object like outside the focal distance. What happens when he goes like way far out? Okay. Let's do the same thing we did with the first one. We'll get the empirical answer first using this right here. I mean, it's the same lens. We use the same lens, but I'm going to look way off the distance. So here's what I do. And well, if you're at home watching this video, then I'm going to hold this up to the classroom. I'm going to pan this around. I'm going to look at you guys through this. You guys are going to look at me through this, and let's see what we see. Okay. So you guys looking through this? I'm looking through. I'm seeing you guys. What do I look like compared to you guys? Upside down? Yeah, am I upside down compared to you guys? Because you guys are upside down compared to me. Ooh, in the physics work, that might be like inverted. Do we both look inverted compared to each other? Okay, so if this ray diagram rules work, then we should see an inverted image. Let's see if we see an inverted image. We're going to use the exact same rules we did for the first one, but we should get a completely different outcome. Okay. Here, I'll draw here's the observer again, eyeball, watch this whole thing. Okay. So one ray parallel to the ground, straight across the top of his head. Zip. Right. You guys can draw, see how those are parallel? You guys see parallel lines? Right. Top of his head. Okay. And that one's gonna refract a little bit here, refract a little bit, and go through this focal point. And so it's the path of that ray of light gets refracted that way. Kind of saw that one. Now it's here. Is that? And the other ray of light we need to make sense of this is we're going to go from the top of his head straight through the center of the lens. And then one might have negligible refraction, so we're just going to get a straight line. And oh, look where those two lines cross. Yep, that totally creates an inverted image. It's the inverted image right there. Okay. According to this ray diagram, it should be like maybe yesterday we were calling a real image too. So that's let me try this pan trick again. So it's around here. This is according to this. Should each look like we're kind of hovering in front of each other. All right. All right there. Okay, so you guys got the first two? That's good. All right, so again, if you are farsighted, you're probably wearing some glasses to correct that. That's kind of some version of this. Okay. Now let's go over to if you're nearsighted, you probably have some glasses that are thin in the middle and thicker closer to the rims. Okay. Oh, I need some focal points for this. I'm going to go maybe like 8 centimeters out, 7 or 8 centimeters, 3, 4, 6, like right there. So focal point, focal point. Okay. But we're just going to do one of these because turns out wherever you put the object for the diverging lens, they have kind of the same outcome. In fact, I'm just going to put the object right on top of one of the focal points. If you want to slide them like a little bit closer, a little bit further away, then it's not going to make that much of a difference for the diverging lens anyway. So we're going to do the diverging right here. Right? You guys got that? So focal points, object, put the object, yeah, kind of anywhere really. All right, we're just going to do one diverging lens. Okay. So let me bring in a ray of light that's parallel to the floor, go across the top of his head. Okay. And that's gonna now this should like diverge, right? So it should like rotate the ruler this way. Okay. Maybe it refracts, once there a little bit, and then when it emerges on the other side, have your ruler lined up with this focal point that well, I drew him like standing on the focal point. Okay. In fact, if you want to, you could extrapolate backwards straight through that focal point. So this observer sees this ray of light, and this guy's brain says, "Oh, well, that ray of light must have come from like back that direction." Okay. All right, we got that. Okay, so ray of light parallel to the ground, parallel, and then it diverges in a way where it could line up with the focal point that I have him standing on. You can extrapolate backwards. A dash line right there. Ever got that? Okay, and then remember the other ray of light we need is from the top of his head straight through the center of the lens. So a straight line, zip. Do you guys see where the image is going to be for that one? Look at where those lines cross. Where the lines cross. You guys can find where the lines cross? The lines cross right here. There is the image. All right, diverging lens. Looks like it's gonna make it look smaller. All right, you guys got all the lenses? The lenses? All right, so let's flip this page over. And on the back, we're gonna do the telescopes. Do a couple of telescopes. I'm gonna split this paper in half. We're just gonna do 2 telescopes. Okay. So the first one's gonna be a refracting telescope. Okay. So it's going to involve refraction, refraction, Snell's law, ray diagram similar to what we've been doing. Okay. But then we're actually going to close this out by going back to reflection. We're going to compare this to a reflecting telescope. That's like where we started this a few days back. Okay. All right. You guys know this like classic like pirate looking telescopes? Okay, look something kind of like this. About. Okay. And this involves a couple of lenses. Now I'm going to do 2 converging lenses, although there's a variation on this where you can do like a converging lens and a diverging lens. So you could do that too, but I'm just going to do 2 converging lenses. Okay. So like way out in the world, and maybe you got like way off in the distance, I'll draw like maybe like a planet like here's like Saturn or something, right? We want to see this. Okay. So this one's called the object lens. It's kind of running out of ink. What's going on here? No, it's got plenty of ink. But okay. And then this one is the eyepiece. Okay. Okay. Oh, so here's the observer right here. Okay, so here's your eyeball, like your observer. Okay. Looking through this eyepiece and trying to like see a planet that's like way off in the distance. Okay. Okay. Now, each of these lenses has a focal length. Okay? Like the object lens, let's have that one is a bit flatter, and so its focal length is like further out, and the eyepiece is makes it curved a little bit more. And if you align those 2 focal points, maybe they like align like right here. So it's like F for the focal point. Here's your focal point. And I'll spell it out. Why not? Focal point. Okay. Now it's really a shared focal point. Right? It's the focal point of the small one, but it's also the focal point of the large one. So what's the rays going to look like? We're going to draw, let's do a few rays. Okay. So say you've got all these parallel rays coming in from like the edge of the universe. Oh, hey, just coincidentally, that matches kind of the width of my ruler. This planet does. So got a couple of rays coming in like this. Okay. Now this top one is going to refract and go straight through this focal point, and then refract, and back parallel. The ray on the bottom goes refract straight through the focal point, and then refract back parallel to this guy's eye. And if you want to, you can throw in a third one and say like, hey, what if one shoots straight through the middle? Well, that one won't refract at all. Like you guys saw yesterday with Snell's law, just 90 degrees to the surface, just straight through. Right? I'll add a little bit more detail here. Let's do this. You just might wonder, like, well, what is magnification on this thing? So I'll call this like f sub o, the focal distance of the object lens, and f sub e, the focal distance of the eyepiece. The magnification for this guy, here. Magnification equals FO over FE. Right? It's just the ratio of those two. So if this is like, I don't know, like 20 centimeters and 2 centimeters, you go, okay, 20 over 2 is, that's a 10 to 1 ratio. So you get 10 times the magnification. Like that. There you go. There's our classic pirate telescope. So these are the telescopes that were around a long time, like Galileo, Kepler. They use like variations of these. Again, you could replace this with the diverging lens and you get a different version of it, but this one's pretty straightforward. Okay. But there is a pretty significant shortcoming with this type telescope, and it involves something you guys saw yesterday. I'm going to flip my screen and remind you guys of something. All right, so you guys remember that right there? You guys remember when you're working with refraction that each wavelength light actually refracts a little bit differently? So the higher frequency, shorter wavelengths like blue and violet refract a lot more than the longer wavelengths like the red. And if you apply that to like this refracting telescope, that's called chromatic aberration. So here, I'm going to jot that down. It's called chromatic aberration. So this observer is not going to see a nice crystal clear planet. It'll be like, well, it's always kind of spread out, right? Isaac Newton was thinking really deeply about this. Say, hey, what if I don't use lenses? What if I don't use refracting lenses at all? What if I use a mirror? And he invented the reflecting telescope. Right, so we're going to go back to reflection. Okay, so let's draw a body of a telescope here. So like right, here's like the eyepiece. Here's the observer for this one. The observer is looking down this way. Okay. All right. So here could be like your planet, like way off in the distance, like crazy far away. You're trying to see this thing. Okay. And now what? Okay, so here comes the light, like parallel rays from crazy far away. Okay. And Isaac Newton said, hey, I'm going to put a concave mirror right here. So this is a concave mirror. Right, you guys see that? Right. And then I'm going to put a second mirror at 45 degrees right here. So this is a 45-degree mirror. It's got a couple of mirrors, a couple of reflective surfaces. Okay. Let's go back. Okay. Let's see what happens to the rays of light. So remember the purpose of this. The purpose of this is that we're getting rid of all this chromatic aberration because there's no more refraction going on. We're going back to reflection. Okay. So here comes a ray of light. And that one gets bounced boing, this way, off this mirror, and that way, okay, like that, boing. Okay. Let's go from the top of the planet, okay. And parallel to that other incoming ray, parallel. Okay. That one's going to get reflected, boing, like this, and into the sky's eye. Okay. And actually, all modern day Sirius telescopes are some version of this reflecting telescope. Okay. So the Hubble telescope, the James Webb Space Telescope that was sent up a little over a year ago, okay, they're all some version of this bottom one that you guys are drawing right now. Yeah, you guys got that? Okay. You need to. Okay. Yeah. So it looks like you guys are finished. I think. If you need to take a quick picture or something, go ahead. You guys know I'm recording this. I'm gonna post this to Google Classroom anyway. Okay. So I think you guys are finished. If you have twins, it'd be great for sometime before you pick out for lunch, and I will give you guys the points for that. If you missed any of those or you need to go back and see them, you can either borrow this one pretty soon or grab it from Google Classroom, turn this in tomorrow. Okay. But these last minutes of class here, I've got some illusions for you guys. Okay, you guys ready to see some illusions? Okay, so I'm gonna switch my screen here, but if you need to borrow that, let me know and I'll let you borrow that. Okay, so switch over here. Okay, and illusion.
I want to start with a game, okay? And to win this game, all you have to do is see the reality that's in front of you as it really is, all right? So we have two panels here of colored dots, and one of those dots is the same in the two panels, okay? And you have to tell me which one. Now narrow it down to the gray one, the green one, and say the orange one.
Right, gray, green, or orange. So that gray compared to that gray, that green compared to that green, that orange compared to that orange. Okay. There's only one match. The other two are off a little bit. Okay. Show of hands. How many guys say the gray matches the gray? Who thinks the green matches the green? And who thinks the orange matches the orange? All right, let's find out.
So by a show of hands, we'll start with the easy green one. So pretty even split. So let's find out what the reality is. Here's the orange one. All right. Here's the green one. And here's the gray one. So for all of you saw that, you're complete realists. All right. So this is pretty amazing, actually, isn't it? Because nearly every living system has evolved the ability to detect light in one way or another. So for us, seeing color is one of the simplest things the brain does. And yet, even at this most fundamental level, context is everything. Okay? What I'm going to talk about is not that context is everything, but why is context everything? Because it's answering that question that tells us not only why we see what we do, but who we are as individuals and who we are as a society. But first we have to ask another question, which is, what is color for? And instead of telling you, I'll just show you. What you see here is a jungle scene, and you see the surfaces according to the amount of light that those surfaces reflect. Now, can any of you see the predator that's about to jump out at you? And if you haven't seen it yet, you're dead, right? Can anyone see it? Anyone? No? Now let's see the surfaces according to the quality of light that they reflect. And now you see it.
All right, rewind a little bit, because if you had any ancestors that couldn't see color, then, well, they're gone from the gene pool. So there you go.
About to jump out at you. And if you haven't seen it yet, you're dead, right? Can anyone see it? Anyone? No? Now let's see the surfaces according to the quality of light that they reflect. And now you see it, right? So color enables us to see the similarities and differences between surfaces according to the full spectrum of light that they reflect. But what you've just done is in many respects mathematically impossible. Why? Because as Berkeley tells us, we have no direct access to our physical world other than through our senses. And the light that falls onto our eyes is determined by multiple things in the world, not only the color of objects,